Hello and welcome back. Today we're going to continue with the computation in our last module here remember that you have a final exam on Thursday. It'll be much the same as your midterm exam. But otherwise we'll go ahead and finish up. Hopefully we'll finish up computation by tomorrow, Tuesday. Leaving Wednesday for a review, and then of course Thursday maybe no lecture, depending on whether or not we get done with a review, so that you have the full day, and extended office hours, of course, so that you have the full day to complete the final exam. But today we're going to continue with the computation. Remember that we are on Piazza, we are on YouTube. If you have any questions, go ahead and shoot. Otherwise, remember that on Friday we looked at this proof using diagonalization, which is due to Cantor. The technique is due to Cantor, and the actual proof with respect to Turing machines, of course, due to, I believe, Turing himself. And he showed that there are languages that cannot be decided by any Turing machine. That's because all Turing machines can be enumerated; they're countable. And the set of all languages cannot be enumerated. They're uncountable. Therefore, there must be languages out there that no Turing machine decides. And remember that decides means that on all inputs, they halt and either accept or reject. They don't go into this infinite loop kind of thing. But that is a non-constructive proof, meaning that we didn't actually construct an actual useful language. We did construct a language to diagonalize against, but what was that language? Who knows? It's non-constructive. It's not an actual language that we could come up with, because of course we were looking at a proof by contradiction. We were trying to reach a contradiction. So the question remains, are there practical problems that no algorithm can actually solve? In other words, for all inputs. Now, there are plenty of problems, practical problems, that are undecided. We call these things undecidable. There are plenty of practical problems that are undecidable in the infinite, right? There's going to be some input that it gets stuck into an infinite loop. But there are, but for all intents and purposes, you can examine, do some static analysis on your code, on your algorithm, whatever you want to call it at that point, and come up with, oh, actually this will get caught in an infinite loop. Did you mean to do that? Right? You can use a linter, you can use static analysis tools to kind of determine that. But unfortunately, there are problems that cannot be decided. We're going to show that one particular problem is undecidable in general. So yes, there are practical problems that cannot be solved for all inputs. And one of those is the halting problem. So the halting problem is, given a Turing machine, M, and an input, X, does M on X halt, right? So the notation here is M sub X. We're running this machine on the input X. Just making sure everything's right. Yep, good. We don't care if it accepts or rejects. We just want to make sure that there is no infinite loop, basically. And so my claim here is that no Turing machine exists to a TM, short for Turing machine, to solve or decide the halting problem, right? That is, we can't create a machine that will take any other machine as input and any other input X and maybe simulate M on X and say, oh, well, if you did that, then it would get caught in an infinite loop, right? For all M and X pairs, that it will necessarily fail on one of those. So our proof is going to be by way of contradiction. And for that, I'm going to go ahead and transition over here to the tablet. And let's walk through this proof, right? By way of contradiction, suppose the halting problem, which I'll just shorthand here, halt, is decidable. Right? This implies that there is a Turing machine, there exists a Turing machine and I'll call it H, that takes any other Turing machine, M, and an input, X, and determines if M, oops, I'll redo this, M on X halts. Right? So what does that look like? Right? So we're just going to say that H takes a Turing machine, M, and an input X, and it outputs, it accepts or rejects. Now remember, H is a machine. It's an algorithm. So it takes an encoding of a machine and an encoding of X and delimits them somehow. Again, it's not that important. You can go ahead and run Huffman coding to come up with an encoding, or if you then this is not I mean, this is not weird, right? You can have a machine run another machine. You can have an algorithm run another algorithm as a subroutine, or take a machine as input. You do this all the time. In C, you have function pointers. So here's a function. I'll hand that off to another function so that it can be used as a callback. Machines run other machines all the time. You can have emulators. You can have interpreters. Interpreters are machines that run other programs. Operating systems run other programs. So it's not that weird that you can have a machine that operates on another machine, right? You can think of it as simulating the computation of that other Turing machine. Anyway, the behavior here is going to be that it accepts if M on X halts, and rejects if M on X does not halt. Right. Now again, I'm supposing that this machine H exists. I'm going to reach a contradiction eventually, showing that no such H exists. So I don't even know, if you were to ask me how this works, I can't give you an answer to that because this machine does not exist, right? Okay. So, consider running H on itself. Right? So, what if I ran, how do I want to write this? Like M on M, right? That should not be weird because what is the input here? It's just a string. It doesn't matter if that string is 1101 representing an integer, or that string is actually a number that represents a Turing machine, because remember, everything at the end of the day is a binary. This is true of even real computers, where everything gets compiled to binary machine code. Right? So all you're doing on a machine is running another machine. You're just feeding it a bunch of ones and zeros, right? And the machine itself is a bunch of ones and zeros. Okay. So it shouldn't be that weird that you can run M on itself. In other words, you can run M on an encoding of itself with itself as input. Right? Okay. Hopefully you accept that. Remember, again, you do this all the time. Operating systems run other machines. You can have emulators where you have a program that is running that is emulating an old Super Nintendo system so that you can play games on your Windows machine. Right? It's not that weird. So now let's go ahead and construct. We will construct a new machine, new Turing machine, Q, as follows. So Q is going to take another machine as input. And how do I want? Yeah, I'll label it as M generically. Right? And what it'll do is it'll simulate the running as just a not even simulate. It'll call as a subroutine basically the supposed machine H that we have because of that exists by way of contradiction. And what it'll do is it'll halt and accept if H on the encoding of M of itself does not halt. There we go. So in other words, it's just going to call this H machine as a subroutine. Think of it as a function. And you've got function calling function all the time. Think of a machine as an algorithm. Think of it as a function. It doesn't matter. Otherwise, it'll intentionally go into an infinite loop if H tells you that M on itself does not halt, or does halt. Right? In other words, accepts. Right? This rejects, and this accepts. So what does Q look like? This we can actually build, right? Here's my Q algorithm. On input, the input is a Turing machine, M, right? And my first line of code here is just going to be simply to call the halting problem on it. Result is equal to H on M. So in other words, encode it. You've already been given the encoding. All you have to do is copy it, make a copy of it as its own input, so that you can ask the halting problems Turing machine, if I were to run M on itself, what would the result be? Is it going to halt or not halt? And if the result is equal to, again, accept, then I'll go into a while loop. While true, do nothing. Any language will allow you to write a loop like that. While one, and then an empty loop body. Else, and here I've run out of room, but that's okay. I will halt and accept. So this is pretty easy to write. This machine actually does exist. It's just 5 simple lines of pseudocode here. Okay. Now, what if we were to run Q on itself? And again, this is not weird. This is not strange. You can open up the Word executable in Word, and you can see that that's kind of like a machine that runs on itself. You can have a hypervisor simulating a bunch of virtual machines. Those virtual machines have a bunch of Docker instances, et cetera, et cetera. And so you have this entire like deep layer of simulation of machine simulating machine of virtual machines, basically. So it happens all the time. What if we ran a virtual machine on itself? What if we ran a Docker instance within a Docker instance? From a practical perspective, you wouldn't want to do that, but you can, right? Just like from a practical perspective, why would you open up the Word executable in Word when it's not a Word document? But nothing's stopping you from doing it, right? So what is the behavior of Q being run on itself? Right. So Q run on itself is going to be, we'll consider this. It's going to halt if H on Q with run on itself. Again, this machine, I'm basically self-referencing here, and that's how we're getting the proof. It's what sometimes is called a strange loop. You're looping in on itself. It's self-reference. That I'm running this machine on itself, and then I'm asking the halting problem. If I were to run myself on myself, what would happen, right? And it halts if the halting problem says that Q on Q does not halt. All right. Otherwise, it goes into an infinite loop if H on Q says it does halt. Right? So we've got a contradiction here, right? Q on Q will halt if this supposed machine H says that it does not halt. right? So and then Q on Q will go into an infinite loop and not halt if H on given Q on Q says that it does halt. Right? So we've got a contradiction here. Q is not the one that we reached a contradiction on here. I was able to build Q just fine right here. Right? What we've reached a contradiction on is our initial assumption that a Turing machine that decides this problem actually exists. So conclusion, no such H can exist. And thus, the halting problem is undecidable. No such machine will decide it for every input machine and every input on that machine. Okay? This is kind of what's called a strange loop. I forget the author's name at the moment who wrote the book, Gödel, Escher, and Bach, but he calls them strange loops because it boils down to something that's very old. It's a nursery rhyme, basically. This sentence is false, right? Or somebody saying, I am lying, right? So it all comes down to self-reference or recursion. I am lying. If I'm lying, then I'm not telling the truth, and so I'm not lying. Right? If I'm so it's a self-referential contradiction. This sentence is false means though it's false, so therefore the sentence is false. Therefore the sentence is true. Right? It's the nature of the self-reference that trips you up here. Right? So because we were able to do self-reference here when running a machine on itself, we can reach this contradiction. Okay, and there are plenty of other practical problems, basically that are undecidable. In fact, there's this larger Rice's theorem that states that in general, if given a Turing machine M, answering any non-trivial property of that language decided by M is itself not decidable. It's undecidable. So if you asked the question of is it finite or is it infinite or any non-trivial property of that language, no machine exists that can give you that answer. Right? Now, again, it comes out of that self-reference. So there are plenty of things that, from practical perspectives, for large enough for all inputs up to a certain size, of course you can simulate them and say no. For all practical purposes, this is decidable for all finite inputs up to 1 million or something like that. But in general, you can't work infinite. You can't answer every single question. So philosophically, philosophy of mathematics is that the Turing machine model is incomplete in that there are things that it can't solve. Right? Okay. So now that we've looked and seen that there are problems that are not solvable or that are not decidable, let's go ahead and start refocusing on problems that can be solved. And we're going to start talking about complexity classes. Right? So among problems that are solvable, right? In other words, decidable, which ones are easily solved and which are difficult or hard to solve? Right? And to answer that question, we need to start capturing notions of work, of resources. And you've seen this before with big O notation, that time is a resource, that memory is a resource. So what does that mean in the context of Turing machines? In a Turing machine, an elementary operation is a transition from one state to another. Right? You can think of this as a clock tick. That's going to be our atomic unit of work as far as time goes. The elementary operation, of course, when you analyze an algorithm, it could be multiplication, it could be division, it could be a comparison. But when you're talking about Turing machines, there's only one thing to look at, and that's a state transition. Now, remember the input, you can read that back and forth. So it's not necessarily an input read or write or an output read or write. It is all transitions, right? Going from one state to the next state until it halts and stops, right? In a Turing machine, the number of output tape cells written to can be considered its memory, right? Resource. So again, the state transition that's for time, basically. That's capturing time, and this is capturing memory, right? For a Turing machine, the input size, right? Remember the 5-step process that I usually give for analyzing an algorithm. Identify the input, right? That's X for a Turing machine. Identify the input size. The input size is the number of bits in the input, which we usually denote as using the absolute value symbols here, kind of misusing them. We'll go ahead and call that n, right? And therefore, you can say that a Turing machine takes t sub n time and m sub n in memory. I don't like that. Let's go ahead and go with MEM to distinguish it from another machine M running something, right? And we're not really going to look at it from the perspective of memory anyway. We're going to focus more on time here, right? You can then bound the number of transitions by a polynomial, or really any other function. All right? So you could say that t sub n, excuse me, there we go, is in order of some polynomial, right? That it's order n to the k, or n to the n squared, or something like that. And that will be our notion of time resources. That'll be our big O notation as far as Turing machines go, excuse me. So this allows you to define complexity classes, right? In particular, P, I wonder if this is going to work. Nope. All right, so math SF. Usually what I do is serif fonts. There we go. P is deterministic polynomial time. In other words, it consists of all problems. Remember, this is a problem class now. Consists of all problems. Remember the equivalence between problems and languages. So languages that are decidable by a deterministic polynomial time Turing machine. Right? There we go. There we go. Deterministic. I think that's spelled correctly. There we go. Yeah. Now the spell checker is okay with it. So remember that we're getting into the P versus NP problem now that you might have heard of. This is P. This is the class of all problems that are solvable by a deterministic polynomial time Turing machine. And most of the problems that we've looked at so far are in P. For example, some examples would include finding the shortest path in a graph, finding the computing a minimum spanning tree. What else have we done? Sorting, right, etc. are all problems in P. These are not algorithms. These are problems. Right? That P and NP are classes of languages. They're classes of problems that have been shown or demonstrated to exist. For example, to show that a problem is in P, there we go. All you need to do is come up with an algorithm that runs in polynomial time. Right? And you don't necessarily have to design a full Turing machine to do this. Any of the algorithms that we've developed in this course so far are enough to show that something's in polynomial time. It's only when you start talking about structural complexity and comparing one class of problems to another class that you need to start looking at it abstractly, because you can't just talk about it in terms of one particular graph problem, because not all problems are graph problems. Sorting is not a graph problem. Computing the determinant of a matrix is not necessarily a graph problem. It's related to graph problems in some ways. But you need to talk about all problems that have a deterministic polynomial time Turing machine that decide them. Right? So what is determinism? I've been throwing that around here now, so we need to define that a little bit. What is determinism? Any computation that has the same result on the same input is deterministic. Right? It's not going to change. It's not random. This is in contrast to something that you might have seen before, randomization. If you randomly generate an input and you do some sort of random sampling or something like that, rerunning it on the same input will not have necessarily the same outcome, because your random bits, your random information might be different each time. Hopefully it's different. Otherwise, then it is completely deterministic and you've got a terrible random number generator. So any computation that basically has the same computation over and over again for the same input. Now, it can behave differently on different inputs. If I give it X versus Y, of course, I would expect maybe there to be a little bit of a difference between those computations. But otherwise, if I give it X and I give it X again, I give it X again, I give it X a million times, the computation will be the same every single time. The result will always be the same, but also the computation of how it got to that result will be the same every single time. So you might have seen randomization. What is non-determinism, though? So non-determinism is basically magic, for lack of a better word. Non-determinism is not a real computational model. You can't build a non-deterministic machine. You can't build a laptop that uses non-determinism. It's more of a mathematical notion that that surprisingly captures a lot of ideas from logic and other areas, and turns out to be really useful for comparing classes of problems to each other. It's not even like quantum computing. You might have heard of quantum computing before, and there are people who are trying to build scalable quantum computers that use entanglement and a bunch of other physics properties in order to do their computations. It's not randomization. Randomization where you generate random bits from a random source, like cosmic background radiation or something like that. It's not randomization. It's not quantum computing. It's not determinism. It's something completely different, right? It is not a real computational model, right? It is a theoretical one, right? No one can actually build something like this, but again, it turns out to be very, very useful when you want to compare computational when you want to compare complexity classes. Okay. So to give you an idea of this, I'm just simply going to provide a visualization. Right? So let's go back over here, and remember satisfiability, or SAT for short. Given a predicate P on, and this is not polynomial time here, it's just P, x1, x2, xn, does there exist an assignment of x1 through xn such that P on that assignment evaluates to true. Right? In other words, does there exist an x1, x2, dot, 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 xn, such that piece of x1, x2, dot, 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 xn evaluates to true? I'll go ahead and just use equals here. You don't actually need that. In logic, that's of course implied. Just similar to if you're coding, you would never actually, again, you call a Boolean function, you would never actually use equals equals true, right? Don't do that. And so this is kind of a bad practice right here, but I just want to be absolutely clear, okay? So here's how non-determinism works, right? One, you have a guessing phase, right? You guess a possible assignment, x1 through xn, right? This is non-determinism. This is this is what makes it powerful. This is what makes it a theoretical model. How did you guess a possible assignment? Don't think of it like randomization. Don't think of it as random. Oh, okay, I'll choose a random bit 0. Okay, next random bit 1. Okay, next random bit 2 or 0 again. Whatever, right? You're not guessing bits. You're not randomly generating these things. You're making a guess, right? 2, verify. If p on x1 through xn evaluates to true, halt, and accept. Right? Otherwise, reject. Now, the acceptance criteria for a non-deterministic Turing machine is different. The Turing machine TM accepts if and only if at least one computation path, I'll put that in quotes here and visualize it here in a second, accepts. Okay? Visually, what does that mean? Now, I've written this out before, but it was because when we were looking at a brute force solution. So x1, you can make that into a 0 or a 1, right? x2, you can make that into a 0 or a 1. And if you made x1 1, then of course you can have, again, two choices over here for x1, x2 as well. x3, 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 and x3. You can make those zeros and ones. And I won't write the entire computation tree here, but what I will do is I'll come down here to the end. Dot, 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 xn. You can make that into 0 or 1. Now, you verify by running, just plugging and chugging. You put a bunch of zeros and ones into a predicate, and it either comes out to true or false. Right? Dot, dot, dot. Now, a guess is equivalent to a computation path. Right? That I'll go through this entire tree and come out to some truth assignment x, okay? And then that gives me a piece of x, and that's either 0 or 1. Right? My acceptance criteria of this entire thing, if there is one, at least one, computation path that accepts. Okay? So the depth of this tree here is the non-determinism. And we're making n guesses. Right? So in other words, it's polynomial. It's not deterministic polynomial. It's not linear in the traditional sense. It is non-deterministic polynomial. Okay? The acceptance phase down here where you verify it, That's, of course, deterministic. Again, because you can take those zeros and ones, plug it into the predicate, and verify whether or not it evaluates to true or false. If I were to give you a truth assignment, then that's pretty straightforward. All you have to do is plug and chug, and you've got your answer. But the key here is it accepts if at least one computation path accepts. In other words, look at this more abstractly here. There is this computation tree, right? And there is a path in this tree. And if this evaluates to true, then it accepts, right? Except if any of these accept, right? In other words, it is harnessing the notion, the notion of the existential quantifier. Does there exist a computation path that accepts? And that's the quintessential notion of the SAT problem, right? The SAT problem is simply, does there exist a setting of Boolean variables that make this out to be true, right? And so what we're doing is we're basically cheating and we're hiding the real work. This is, if you were to actually do this deterministically, right, brute force, you would have to backtrack, or generate every single one of these exponentially many computational paths. How many are there? Well, there are going to be 2 to the n possible paths. So we're kind of cheating here and hiding the exponential the time that it would take to do this deterministically in the existential quantifier here. How powerful is that existential quantifier in logic? It turns out to be pretty powerful, right? That we don't know how to simulate that without blowing it up and having an exponential algorithm to do that in our deterministic model. Okay, so again, to review here, all non-deterministic algorithms have 2 phases. The first phase is the guessing phase. You guess a solution in non-deterministic polynomial time. Right? Then you verify the solution. Right? This is you accept if it is valid, and these are usually called certificates, making the guess a certificate of authenticity, basically. Yes, it is satisfiable. Here's your certificate, right? Here's the actual setting of Boolean values that would make it evaluate to true, right? You accept if it is valid, and the machine overall, the machine accepts if at least one computational path accepts, right? Again, that's why I called it magic, because it's not parallel computation. We're not farming each one of these paths out to an exponential number of processors or an exponential number of Turing machine subroutines or something like that. By magic, it can look at all exponentially many computational paths, and it can say accept or reject immediately, right? That's why it's not a real computational model, but it is a theoretical one, and it turns out to be a powerful theoretical one because it encapsulates exactly what our notion of an existential quantifier in logic. You might also be thinking about a universal quantifier for all x. Does the predicate hold? Right. That's a complexity class called co-NP that we won't get into here, but this does allow us to define NP. Right. So let's see. Here, I'll just cut and paste this since we're good on time. There. The set of all languages L that are decidable by a non-deterministic polynomial time Turing machine is called NP. And it doesn't stand for non-polynomial. That's a very, very common mistake. So don't feel down on yourself if you've thought that before or you made that interpretation. It's non-deterministic polynomial time. It is this magical, unreal, theoretical computational model, right? Don't think of it as real at all. You can simulate non-determinism very, very easily. All you have to do is brute force it. And once you've got brute force, though, now it's exponential time. Non-deterministic polynomial time is polynomial time because it only takes a polynomial number of guesses to get a possible solution. The verification, you verify each one in deterministic time, but the overall machine accepts if there exists a computational path that accepts. You don't look at over all 2 to the n computational paths at the bottom of that computation tree. You just magically accept if one of them does. Okay. So, comparison. The P versus NP problem asks, is P equal to NP? Yeah, I'll put it in one row here. Or not. Right. They're not. Are they equal or are they not equal? I don't know why that's not. Maybe I have to go like that. There we go. Or not. Right? They're not equal. Now most believe they are not equal. Right? That an exponential amount of time is required to simulate non-determinism. An exponential amount of deterministic time is required to simulate non-determinism. It's really easy to see that one is contained in the other. It is easy to see that, and I'll go ahead and cut and paste this here. It's not equal, but it is a subset that may be equal. We just don't know. There we go. Why? Well, if a problem is in P, then it's certainly in NP, because you don't use any non-determinism. Non-determinism seems to be a little bit more powerful, but we don't know the other way around. Is P contained in NP, or is NP contained in P? That would imply that P is equal to NP. Most people don't think that. Most people think that there are problems. Most think that there are problems that are in NP there you go. Problems, languages again, NP that do not have a deterministic polynomial time solution, right? Or algorithm, right? Or Turing machine, again, these are all equivalent. So mind my spelling here, but what does that mean? Well, let's look at this from a complexity landscape. So what I mean by that is let's draw out P and NP here. This is NP. And P is easily seen to be contained in NP. There are some problems here, for example, minimum spanning tree, right? Or shortest path, right? Or other problems in NP sorting, or sorry, P sorting, etc. Right? What are some problems over here in NP? We've seen some of them before. For example, SAT. Right? We've seen other knapsack, 0-1 knapsack. Remember when we looked at the dynamic programming solution for 0-1 knapsack, it came with a caveat that it was pseudo-polynomial time. It was not actually in P, because if the weight were exponential, then that means that we would end up having an exponential time algorithm. And by the way, you can have bigger complexity classes. For example, exp is basically any problem that is solvable by a deterministic Turing machine that runs in exponential time instead of just a polynomial time. And NP is contained in that because we can always simulate a polynomial amount of non-determinism by doing brute force exponential algorithms. That goes beyond what I want to cover here, so I'll go ahead and just mention that that exists. I want to keep our complexity landscape here simple. All right, so how do we even go about beginning to answer this question of, are they equal? In other words, does this entire thing collapse down to P? What we need is a way of comparing, not algorithms, but comparing problems. We already know how to compare problems to algorithms. To compare algorithms, you use big O analysis. For example, merge sort. That's going to be order n log n. Pretty good. Quasi-polynomial time. Selection sort. That's going to be order n squared. Not as good, right? But both of these are still in P, right? I shouldn't say that they're. Don't think of them. Sorry, I shouldn't have said it that way. These are algorithms, and algorithms are not the same thing as problems. And hopefully you understand that by now. Why? Because Turing machines, which are algorithms, are not the same thing as languages. Turing machines decide languages. Algorithms solve problems, but they're two completely different things. These two things right here are algorithms. What is the problem itself? The problem is simply sorting, right? So when I wrote sorting down here, how did I know that it was in P? Well, the existence of either one of these deterministic sorting algorithms says that this problem is in P. So how do I show that something is an NP? All I need to do is come up with an algorithm, a non-deterministic polynomial time algorithm, to show that it is an NP. That's what we did over here, right? All you have to do is guess a possible assignment, verify, and accept or reject. That was enough to show that it's in NP. 0-1 knapsack problem, you guess a certificate. You guess a subset of elements, and then you add them up, and you have to use, of course, decision versions of these things. And so you need to look at a decision version of the 0-1 knapsack. But that's the basic idea, right? In fact, all of these are part of a elite class, I guess you could say, called NPC. This is NP complete problems, right? So to get back to what I was saying before, to compare algorithms, you use big O analysis. That merge sort is better than selection sort because it has a better running time. But what if I were to compare two problems, right? Sorting versus, I don't know, SAT, right? Which one is inherently harder? Right? We know that sorting is in P. We know that SAT is in NP. But how do we? So I mean, we know that SAT is at least as hard as sorting. But one, how do we know that? And two, how could I potentially show the other way? That these two things have an equivalent difficulty? Equivalent difficulty? Or one is harder than the other. The mere existence of algorithms to solve them doesn't answer that question. Instead, what we need is a way to compare this complexity class with this complexity class. And the idea that we are going to use is called a reduction. Now, unfortunately, it is a terrible, terrible name. I didn't name it. I think there should be a much better name for it. When you typically think of a reduction, you're thinking of taking something that is complex and you're making it simpler. You're reducing it down, right? You're lessening it. That is not what we're talking about here, right? So again, what is our goal? Our goal is that we want to establish the relative complexity of problems, not algorithms. Right? The inherent difficulty of problems, not the behavior of actual algorithms. Because nobody knows a polynomial time algorithm for 0-1 knapsack problem or the SAT problem, right? Relative complexity of algorithms can be done with big O analysis, right? What we want is, you can come up with big O analysis and come up with an upper bound or whatever, but what we want to deal with problems, or again, languages, not algorithms. So the framework we're going to use is called reductions. In general, you can use or adopt a supposed solution for one problem, B, to solve another problem, A. Now, I'm going to show you this to you with a concrete example soon here, but you do this all the time. I want to solve one problem. I don't know how to solve that problem, at least fully, but I've got this off-the-shelf solution over here. This is something I try to drive into heads in the first few weeks of Computer Science 1. What's the first question you should ask yourself when you are faced with a problem? Is this problem already solved? Or can I use an off-the-shelf solution and adapt that to solve this problem? Don't try to reinvent the wheel. So when I'm looking at a problem A and I want to solve it, that seems like a lot of work. Maybe if I could use this solution, off-the-shelf solution over here to B, then I can solve A, right? And if I can do that, then I can come up with a relative complexity of those two problems. A is no more complex than B. Or another way of putting this is that A is no harder to solve than B. Or another way of putting putting it again is that B, from the other perspective, the reverse perspective, is just as complex or even more complex or hard to solve than A is. Right? We are not making A simpler. Right? Intuitively, we are reducing A to B. Right? We're not we're reducing it. We're not reducing a hard problem to a simple problem. We're not reducing a simple problem to a harder problem. That's not the way that you should look at it. Right? The way that you should look at it is simply that you're using this thing as a subroutine. Right? So again, you have this idea. I don't know how to solve A. But if I know how to solve B, but if I could solve B, I could solve A. Right? So I've reduced the problem of solving A to the problem of solving B, right? And the notation that we use for that is simply just that A is less than or equal to B by some resource measure. And in this case, we're going to look at polynomial time reductions. So I'll use it like this. P, capital P, right? I like that notation better than actually calling these things reductions, because it sets up a relative difficulty of problems, not a relative complexity of algorithms, a relative difficulty of problems. B is at least as hard as A. I've reduced A to B, right? Sometimes I mix those around. We're reducing A to B, right? We're not making it more hard. We're just saying that B is at least as hard as A is, or A is no harder to solve than B. So think of this as a less than or equal to, and think of it in terms of hardness. If I say that A has hardness or difficulty 5, then B has hardness difficulty at least 5, right? Whatever 5 is, right? whatever made-up units you want to come up with. So let's look at a motivating example from something that you would clearly be able to do right now in Python, right? So, motivating example, right? Essentially, reductions use other algorithms to solve other problems, right? Reductions, there we go. Right, I'll come back and make sure I spell check everything later on. Right? So here's a motivating example. Right? So given a graph G and two vertices X and Y in G, right? We can ask several questions. Is X connected to Y, right? And this is the is connected problem, right? You can use DFS, BFS to solve this, right? But again, we're not looking at algorithms, we're looking at problems. That is an algorithm to solve this problem that we know about, but I want to look at three different problems here. What is the length of the shortest path X to Y? And it can be directed or undirected, it doesn't matter. This is the shortest path length problem. And again, we know how to solve this, right? All you have to do is run Dijkstra's. With X as the source, find Y, and then report the length of the path or the weight of the path if you're looking at a weighted graph, connecting them. Right? If there is no such path, then of course you can report that it's infinite. Right? Another third problem is, what is the shortest path? In other words, given X and Y, I want you to actually output a path, okay? And this is the shortest path problem. Right? So what is the relative difficulty of these three problems? Which is the hardest to solve? Okay? So I'm going to introduce this notion by simply just writing some Python code here. All right. Now, let me think. I'm in a world now where I don't know about anything about Dijkstra's. I don't know anything about Floyd-Warshall. I don't know anything about DFS, BFS, or anything else. I don't know. I only know these three functions. Is connected, given G, X, and Y, determines if, and like here, I'll make it bigger. It determines if there's a path from X to Y in G. Those are the arguments, and it returns true if a path exists between the vertices X and Y in the graph, false otherwise. Shortest path length takes the same exact input, but instead of returning true or false, it returns an integer representing the length, the number of edges, of the shortest path between X and Y. 0 is returned if X is equal to Y, and -1 if no such path exists. So we're always going to be returning an integer from this function. Shortest path. A list will be returned representing the sequence of vertices in the shortest path between X and Y. None is returned if no such path exists. So which one of these should we write first? Should I immediately say, okay, well, is connected, I'll go ahead and write BFS, DFS to determine that, whatever, right? Stop, back up a second here. All right. Again, what's the first problem? What's the first question you should ask yourself when problem solving? Does a solution already exist? So let's assume that shortest path length here, somebody else wrote that, or that's part of the graph NX library, right? How could we use that in our solution to is connected? Right? So remember, it returns 0 is returned if X is equal to Y, and -1 if no such path exists. So let me go ahead and write this Python code. Right? If I'm going to go ahead and k is equal to shortest path length, passing it the same arguments x, y, g, x, and y, right? If x is, or if k is equal, is less than or equal to 0, I'll actually no, if it's 0, 0 is returned. So if it's 0, then I'll return 0, right? Now why? It's because x and y are the same variables, or they're the same nodes, and so I could have made this check up front instead of calling shortest path length, and that means that you have that they are connected because they're the same thing. If you're at x and you want to get to y and y is x, just stay where you are, right? So return true. Sorry, right? Else if, or else if k is equal to -1, then I'll return false. Else return true. Right? Again, it returns -1 if no such path exists. So is connected will be false if it's -1. It'll be true otherwise. And so now I can actually simplify this greatly. All right. So if it's -1, return false. Otherwise, for all other values, return true. Right. And now you can simplify this too using a ternary operator or just a simple return statement. So what did I just do? I solved the is connected problem by using a solution to the shortest path length problem. In other words, I punted. I didn't know how to solve this problem, but I had a solution to that other problem over there that I could adapt. So I'm not going to solve that problem. I'll just use that off-the-shelf solution, adapt it by checking its return value, and then returning my own return value of true or false. Right? That means that is connected is no harder than shortest path, right? Path length in this case. In other words, here's my picture. Again, it's is connected, shortest path length, and shortest path. So is connected, I reduce that to solving the shortest path length problem. Right? In other words, this is no harder than this one over here. Because if you have a solution to the shortest path length problem, you have a solution to this one over here. Right? Again, I don't have a solution for that yet, so let's go back to the drawing board and let's pick up a solution for that. Again, I'm going to punt it. Right? Shortest path length will simply be, I'll call P is equal, and that's for path, not polynomial time, shortest path, G, X, and Y. There we go. That returns a list, remember? It returns a list representing the sequence of vertices in the shortest path between X and Y. None is returned if no path exists. So how do I determine whether or not there's a path? Well, it returns -1 if no such path exists. So I'll just simply if P is none, return -1. Else, return the length of the path. Now, I'm assuming here that if X and Y are the same, then it will return an empty list. All right, we didn't put that down here. If no such an empty list, if it only has the vertices in between them. So if there are no vertices in between them, then it's length. I guess it's going to be the length of +1, right? Because if I go from A to Z and I have to go to X to Y and I have Z in between, then the list will only have one element, but the path is going to be length 2, right? So I've punted again, right? And I've done another reduction. Shortest path length is no harder than shortest path. Now this is just a motivating example here, right? This is actually a decision version. This is a decision problem. This is an optimization problem. And this is a functional problem. because this one actually needs to report and build a solution. This one just needs to return a number representing the optimal solution. And this one is just simply returning a yes or no answer, that there exists a path or not. But you can see the sequence of difficulty. In fact, you can actually show it's circular here. You can reduce the shortest path problem all the way back to is connected. But everything in here is in P, right? All of these problems are in P. Right? Strictly speaking, P and NP only deal with decision problems. So when you reduce one problem to another problem, you have to show that this decision problem reduces to this decision problem. You can't mix and match functional and optimization problems. Technically, you can't do that. But from a practical perspective, you can. Remember the trick that we did, right? That we'll translate this into a decision version by simply just taking G, X and Y, and K, and asking, is the shortest path X to Y? I'm not asking for the optimal K. I'm just asking, all right, here's the input, 5. Is it 5? Is it 6? Is it 4? Is it 3, 2, 1, right? Have, or does, I guess, length K. And now I've taken an optimization problem and I've changed it. It's not really a reduction, but I've changed it to a decision version. So those are just technical details that we can gloss over and not worry about. Right? Visually, what does that look like? Again, I just showed you a bunch of Python code. Here's what the visualization looks like. Reduction. There we go. Now this is a mapping reduction, which we'll talk about next time. But it's the same basic idea. Right? B on Y is my off-the-shelf solution for B. What I'm doing here is I'm reducing a problem A to a problem B. Right? And I'm keeping it general now and generic. A is a problem. Is it the 0-1 knapsack problem? Is it the sorting problem? Is it the is connected problem? I don't know. I don't care. I want to talk about these things in general. Right? I am reducing A to B by coming up with a solution for A given a solution for B. So again, I don't know how to solve A. This is a black box here on how to solve A. X is an input to A. So what I'll do is I'll go ahead and put this through what's called a mapping function. And what I did over here, it's Python code from before. What I did is I took A and or X and I simply just called another function basically, producing a result Y. And then I put it into another, I'm mixing that up here a little bit, but it's the same basic idea. The idea here is that I don't know how to solve this problem. I don't know how to solve A. Oops, sorry. I don't know how to solve A, but I do know how to solve B. And I also know how to translate instances of A into instances of B by putting it through this mapping function. Once I've got Y, all I need to do is input it into this black box that I have for B that somebody else wrote, NetworkX wrote it for me or whatever, and take and say, well, if that says yes, I'll say yes. Again, these are decision problems, yes or no. If it says no, I'll say no. And you can this is the visualization of it, but you can go ahead and think of this also as pseudocode. Oops. What does this look like pseudocode wise? Right? Here's my algorithm for A. On input X, or the input is X, excuse me. What I'll do is I will translate into this Y by putting it through this function, this mapping function. My reduction. This is the actual reduction. This is the mapping reduction. And then I've got Y now. What I'll do is I'll put in a result by calling B on X. Or, sorry, Y. And then I will simply say that if B, or if result, then output yes. Halt and accept, right? Else, output no, right? I could simplify that greatly, of course. Oops, I don't want that much erasing. There you go. By just simply returning b sub x, b sub y, excuse me. All right. Let me make that absolutely clear that we're running b on y. All right. So again, if I have a library function for one problem, and I can use that and adapt it by putting it through this mapping function here. The mapping wasn't, strictly speaking, the mapping that we did in our Python code up here wasn't a pure mapping. This would be what's called a Turing reduction. These are not mapping reductions, but we'll talk about mapping reductions next time. What I'm doing is I'm using the solution to one problem that is output by this other algorithm, and I'm changing its output to produce a solution to another problem. Right? And that's the basic idea. I like to start out presenting reductions like this simply because everybody is familiar with this. If you're a good coder, you do this all the time. I don't know how to solve that problem, but NetworkX has this method over here that I could use. I could use that method as a subroutine, and then I've got my problem solved. Right? Again, be lazy. Good coders. What the hell are we doing this for to begin with? We're automating tasks. So why wouldn't you automate your own tasks by simply just reusing what you have from a library? Okay. I see no questions here. So I'll give you a preview of next time. Next time we're going to be looking at mapping reductions. Right? That was just a motivating example. But polynomial time mapping reductions. And sorry, let me come down here. Polynomial time mapping reductions. Right? Ultimately, we want to map input instances of one problem to input instances of another problem. Right? You can look, ultimately, you can look at Turing reductions like we've just done there we go. You can look at Turing reductions like we've just done. Those are the most general types of, well, you can get even more general than that looking at, but you're basically using the power of any Turing machine. We want to restrict our power. We want to be as restrictive as possible. In other words, we don't want to use more power than we have in our complexity class to cheat and solve the problem and then trivially map it to a yes or no solution. Right? What I mean by that is, think about the following reduction. How do I sort an array? Oh, well, you call qsort. Right? Well, okay, yeah, from practical perspective, that's what you do. That you don't roll your own sorting algorithms. But if I'm talking about how do I solve this problem, right? You need a little bit more meat in there. You need more pseudocode. You've trivialized the problem by simply just repeating me, right? While you sort it. How do I sort? Well, you sort it. How do I solve the 0-1 knapsack problem? Well, you just solve it, right? We don't want to use the power of nondeterminism to solve our problem for us. So we want to restrict ourselves and say, you can't use qsort. You can't use the solution to satisfiability in order to do this, right? In order to transform your problem. For example, to solve satisfiability, I'll use this solution for sat over here, and then if it outputs true, I'll output true. If it outputs false, I'll output false. No, you have to restrict your power a little more than non-determinism. So in other words, we're not going to use non-determinism in our mapping, right? Ultimately, what we want is a deterministic mapping. We only want to use the power of polynomial time deterministic algorithms to compute our mapping. We don't want to cheat. We don't want to suddenly use any Turing machine, which could happen to be a non-deterministic polynomial time Turing machine, to cheat and solve our problem directly. Okay, so for that, we're going to have to talk about mapping reductions. That I'm going to map instances of sat over to the instances of this problem over here. Or one graph problem can be transformed into a different graph problem. Right? And so that if you have a solution to this problem, then you have a solution to the original problem. Okay. that's where we'll pick it up and finish hopefully tomorrow. Right? Otherwise, I'll see you in office hours.